Sun. Today I will be talking about Puma, a programmable, ultra-efficient memristor-based accelerator for neural networks. To start, we have the knowledge gap and the research goals. Existing designs do not provide flexible data movement and control operations to capture the variety of access and reuse patterns in different workloads. As general purpose computing systems approach their energy limits, domain-specific architectures have captured this interest, specifically machine learning workloads. Moving on to the memoristic crossbars. These store matrices with high storage density. They perform matrix vector multiplication with very low energy and latency, as opposed to the many steps it takes with digital logic, and it combines the compute and storage into a single device. This has intrinsic sustainability for data-intensive workloads. Next are the prior designs. Prior memoristic crossbars support one or two kinds of neural networks, but this lack of general support is not scalable to a large variety of workloads. Existing accelerators lack the toolset for general machine learning workloads. Long short-term memory workloads require multiple functions that cannot be executed on crossbars efficiently, as an example. And designs do not provide control operations or flexible data movement, and data movement can amount to a significant portion of total energy consumption. And furthermore, unique to crossbars have a high write latency, opting to store constant data while variable inputs are routed between them. So addressing these limitations with Puma, Puma is first designed to preserve storage density of memoristic crossbars. This enables mapping machine learning applications using on-chip memory only. It's designed to supplement crossbars with an instruction execution pipeline, and it utilizes special ISA. The specialized ISA enables compact representation of machine learning workloads with low decoder complexity, and it utilizes temporal SIMD and ROM embedded RAM, and these are used for area efficient vector computations. And all of these are co-designed to optimize data movement and to maximize energy efficiency. Oops. And Puma microarchitecture is compatible for recently fabricated crossbars. Next is fabrication. Our key contributions lie in the core architecture and the tile architecture that bring programmability and generality to memoristic crossbars without compromising their energy and area efficiency. Matrix vector multiplications are the dominant operation in multilayer perceptrons, which make memoristic crossbars suitable for acceleration since their matrix vector multiplications have low energy and latency. Crossbars capture high data parallelism in multilayer perceptrons. Complementary metal oxide semiconductor implementations suffer from excessive DRAM accesses, which are particularly expensive from the lack of data reuse. Memoristic crossbars can treat matrix-matrix operations as successive matrix vector multiplications. This takes advantage of the input reuse to minimize the movement of data within the chip. And finally, there's non-sequential access. This is due to the way the inputs are traversed, and an implication, however, is needed to support fine-grained and random accesses to memory. Next is the workload characterization. There's support vector machines followed by recommender systems. These compute weighted sums followed by nonlinear functions. There are recurrent neural networks used for sequence processing to compute weighted sums on input and previous state. And finally, there's general adversarial networks. These are made of two neural networks that compete to reach equilibrium. And then there are restricted Boltzmann machines and Boltzmann machines, and these are used in unsupervised learning tasks for energy minimization. The core architecture for Puma utilizes a vector functional unit design based on temporal SIMD. So the they balanced out the size of the vector functional unit because too wide of a wide vector instructions reduce instruction storage overhead, but narrow vector functional units prevent offsetting the area efficiency of crossbars. The vector functional unit To solve this, the vector functional unit executes wide vectors over multiple cycles, and they implemented the narrow functional unit in order to maintain area efficiency. Furthermore, the ROM embedded RAM is used to effectively store lookup tables, and ROM embedded RAM is used as a digital alternative. It uses an alternative to used as alternative digital implementations that have high area requirements that would offset the low crossbar area. The instruction As spatial architecture, Puma is organized into three tiers: cores, tiles, and nodes. The instruction execution pipeline is a simple in-order pipeline. The stages are fetch, decode, and execute. This pipeline is designed specifically to save area. The input registers can be rerouted to enable logical input shuffling without physical data movement. For larger models, due to their size, they may scale to multiple nodes, and data can be routed between crossbars and Puma, which each crossbar storing a different portion of the model. This is the core architecture. As you can see, the XBAR in register. These are the XBAR in registers that can be rerouted to enable logical input shuffling without physical data movement. The register file permits buffering in general purpose registers. This avoids higher cost access to shared memory, and if the register file were too large, it would degrade core storage density, which is why the goal is to make it as small as possible. Instruction set architecture and functional units can be used to allow matrix vector multiplications to support differing workloads, and these support a larger variety of workloads, which creates high decoding complexity. For tile architecture, tiles are made up of multiple cores and are connected to shared memory. One principle for shared memory is intercore synchronization. The second principle There are two attributes per data entry. This utilizes two attributes. One principle for shared memory is intercore synchronization. This utilizes two attributes per data entry for safety reasons. The two attributes per data entry are valid and count. This ensures that producer cores do not overwrite unconsumed data, and permits consumer cores to block until producer cores have written their values. The second principle is sizing the shared memory. As a large shared memory degrades crossbar storage density, Puma utilizes intercore and intertile pipelines to exploit the interlayer parallelism. These pipelines are used to maintain throughput and keep the shared memory size small. Next is the tile architecture, as you can see here on the right. A receive buffer enables data to be received independently of receive instruction, and this is important as receive instructions are executed in a blocking manner for simplicity. Next is the compiler. It is not scalable since it's not scalable to write different code for each core or tile in each input set. That's what the compiler does. The steps in the partitioning process, which is the first step for the compiler, are graph partitioning, where the compiler divides tensors into two tiles the size of the one matrix vector multiplication unit. Next is hierarchy partitioning. The priority groups matrix vector multiplication units that feed into the same outputs together. Next is the insertion of load and store operations. When inserting load and store operations, the compiler also assigns send and receive operations. And next is the instruction scheduling. It's used to reduce register pressure. The linearization of the subgraph for Puma involves prioritizing consuming produced values before producing new ones. Capturing instruction level parallelism of matrix vector multiplications. The compiler fuses independent matrix vector multiplication operations on differing units into the same core in a technique known as matrix vector multiplication coalescing, which is desirable when two multiplication results are to be consumed soon one after another. Next is the last thing is avoiding deadlock. Cycles introduced by improper linearization can cause deadlock, which is why the entire graph is linearized at once. And here's an example of deadlock, where there's data dependence on prior nodes and there's control dependence on later nodes, and as a result, it can't continue because it's kind of like an algebraic loop where you need to know the output to know the input, but you need to know the input to know the output. And as a result, it's this algebraic loop that isn't broken. So instead, they use this architecture over on the right to prevent deadlock. Next are the results and evaluation. Puma can achieve significant improvements compared to state-of-the-art CPUs, GPUs, and ASICs for machine learning acceleration. The evaluation methodology was that Puma was used to evaluate performance in PumaSim was used to evaluate performance and energy consumption. The core data path was designed at register transfer level in Verilog HDL. Synopsys Design Compiler measured the area and power consumption for silicon optical interconnects, and Cacti 6.0 was used to measure memory modules. For inference energy, Puma displayed sizable energy reductions across all benchmarks. This is thanks to its lower matrix vector multiplication compute energy and lower data movement energy. It has 11.7 to 13 times. It's 11.7 to 13 times more efficient than Pascal in computational neural networks. It's 30.2 to 80.1 times more efficient than Pascal in multilayer perceptrons. It's 2,302 to 2,446 times more efficient than Pascal in deep long short-term memories, and it is 758 to 1336 times more efficient than Pascal in wide long short-term memories. CNN showed the least energy reduction as they have a lot of weight reuse. This limits Puma's energy savings from the use of crossbars for matrix vector multiplication computation, and the large matrices in wide long short-term memory can span multiple Puma cores and tiles, which makes deep long short-term memory more appealing for Puma architecture. Here's a graph of inference energy. As you can see by the dark colors here, Puma has the lowest normalized energy compared to its competitors, specifically Pascal, which appears to be the second best in all metrics. Next is inference latency. Puma displays lower latency across most platforms. The exclusion are certain multilayer perceptrons on some GPUs. This is because multilayer perceptrons have no interlayer parallelism for spatial architecture pipelining to exploit. So it has a 2.73 to 2.99 times. It's 2.73 to 2.99 times faster than Pascal in CNNs. It's 41.6 to 66 times faster than Pascal in deep long short-term memories. It's 4.7 to 5.24 times faster than Pascal in wide long short-term memories, and unfortunately, it is 0.24 to 0.40 times faster than Pascal in certain multilayer perceptrons. As mentioned earlier, because multilayer perceptrons don't have interlayer parallelism. So Puma's latency improvements come from the lower matrix vector multiplication compute latency. There's no wait data access latency because it's already in the crossbar, and the spatial architecture pipeline exploiting interlayer parallelism. Here is the inference latency. Here's the inference latency. As you can see, Puma unfortunately Puma is somewhat second or third in multilayer perceptrons for the reasons disclosed earlier. However, in all other metrics, it is clearly shown to be superior. Next are the machine learning accelerators. Against tensor processing units, Puma displayed an 8.3 times higher peak area efficiency and a 1.65 times higher peak power efficiency. Against Isaac, Puma displayed a 20.7 lower power efficiency and a 29.2% lower efficiency. Puma displays lower power and area efficiency than Isaac because of its overhead of programmability, and despite this, Puma can still achieve energy gains over GPUs with tensor cores. This concludes my presentation for EE509 over the Puma architecture for presentation assignment number 6. Thank you for your time.